We will start the session in 2 minutes. We'll start now. Good afternoon, everyone. So, myself Ankara. I am a research scholar from Department of Chemical Engineering, IIT Hyderabad. So, I'll be handling these problem solving sessions. So, I have been doing it. So, now we are in week 8 for this problem solving session for the NPTEL course Computational Fluid Dynamics, and course code is NOC25CH18, and the course instructor is Professor Sreenivas Jayanti sir from the Department of Chemical Engineering, IIT Madras. So we are almost covered 2/3 of the course since we are in week 8, and in today's class we'll be dealing about solution for the Navier-Stokes equations for the incompressible flows, and yeah, we'll start it. So before moving into the problems for this week's, let us just have a brief idea of what we have been learning and what we will be covering. So since this computational fluid dynamics course is a 12 weeks course, so in the first week it is about introduction to the calculation of flow in a rectangular duct, and in second week it is about calculation of fully developed flow in a triangular duct. So in the first week we saw about how to get the solution when we are using a finite difference approach, and in the second week how to use finite volume method to deal with such problems we have seen, and later on we have moved on to derivation of equations governing fluid flow. So why are we interested in CFD? Because we will get the solution in a better way and with less expense compared to the experimental things. So what we do is we generally solve for the equations, flow equations in that system. So what equations we solve? We solve for the continuity equation and the momentum conservation equations when we are dealing with a simple flow case. So we have seen about what those equations are, and in addition, if we are dealing with energy mm, involvement in the system or any reactions taking place inside the system, we will be solving additional energy conservation equation and species balance equation as well. And in week 4 it is about equations for incompressible flow and boundary conditions. So as I mentioned, when we are dealing with flow system and that particular flow, we solve for the equations, but we will be giving certain initial values and certain boundary values. For example, if let us consider a pipe flow, water flow in a pipe. So we will be giving at the inlet the velocity is so and so condition, and at the outlet it is open to atmosphere, so pressure is this. So these kind of boundary conditions we will be giving, and there are two types actually, Dirichlet and Newman boundary condition, and combined mixed boundary conditions also exist. And later we saw about basic concepts of CFD, finite difference approximations, and also we saw about the consistency, stability and convergence, which are like very important when we are doing CFD study, because all the time we would not get a proper solution. So we should have some criteria, and we for us to get the stable solution, because these simulations in if will depend on system size. But if it is a larger system of industrial scale, or there will be the we will be solving these equations in small grids, right? So if number of grid size will be increased when system size is large, and because of that it will take a lot of time to get the result. So when we are not imposing these criteria, the chances are there that it will run for a very long time, and at the end we will get a wrong results, or even it will run for a quite a large number of time steps, and afterwards it will lead to divergence. So these issues are there. So we need to ensure that the system we are dealing with will give a consistent, stable and converged solution. So these are the basics, and in last week we have seen about the solution of Navier-Stokes for compressible flows. So basically we have seen about when we call the flow as compressible flows, when we call it based on the Mach number criteria. Like if Mach number is less than or equal to zero point 0.3, we call it as incompressible flows, and if it is greater than 0.3 we call it compressible flows. So those things we have seen, and also we have seen about a solution of Navier-Stokes equation for compressible flows by various methods like McCormack method and beam forming method, so on and so. So in today's class what we are going to do is we are going to deal with problems involving solution of Navier-Stokes equation for incompressible flow systems. And in further weeks we will be solving problems related to solution of linear algebraic equations using basics and advanced methods, and finally it is about finite volume method including grid generations, and at last it is turbulent flows and turbulence modeling. So turbulence modeling is quite complicated because it involves additional variables, like there will be eddies, there will be like turbulence, so we need to ensure proper modeling is considered. And for the books and references, we have 5 books. First is Ferziger and Perick, Computational Methods for Fluid Dynamics. And second one, it is Hirsch, Numerical Computation of Internal and External Flows. And third one, it is Patankar, SP, Numerical Heat Transfer and Fluid Flow. And fourth, it is Versteeg, Malalsegara, an Introduction to Computational Fluid Dynamics using Finite Volume Method. And last, it is Anderson JD's Computational Fluid Dynamics, Basics with Applications. So we'll go to today's problems. So as I mentioned in today's class, mostly we will be dealing with a solution of Navier-Stokes equations when we are dealing with the incompressible flows. So what do we mean by incompressible flows? We call it incompressible flows when Mach number is less than or equal less than 0.3. So now we will move on to problems. So this is our question 1. So in question 1, what is being asked? For 3-dimensional incompressible flows, the minimum number of partial differential equations to be solved is dash. For 3-dimensional incompressible flows, the minimum number of partial differential equation to be solved is dash. So in last week, we dealt with a similar problem. In that, instead of incompressible flows, it was asked about compressible flows. So what did we do? For 3-dimensional compressible flows, how many partial differential equations do we need to solve? So the first one was continuity equation, and since it is a 3-dimensional problem, we had x momentum, y momentum and z momentum, 3 momentum conservation equations. And also since the flow was a compressible flow, we had to deal with energy conservation equation as well, because density variations were quite high and we need to include energy conservation equation. So on the whole it became 5 equations, 5 partial differential equations which we need to solve to get a solution in a 3-dimensional compressible flow. I am talking about compressible flows. So in this week, since we are dealing with the incompressible flows, how many do we need to solve? Like continuity equation remains the same. We need to solve for the continuity equation, and since it is a 3-dimensional problem, we will be having x momentum conservation equation, y momentum conservation equation, and z momentum conservation equation. So 3 momentum conservation equations will be there along with one continuity equation. And in incompressible flow, what happens? There will not be much variation in the density in the system. So we need not solve for the energy balance equation. So we have 1 plus 3, 4 partial differential equations which we need to solve. So now let us look at the options first. So option A 3, option B 4, option C 5, option D 6. So as we discussed, we know the answer as option B because we are dealing with incompressible flows and the system is a 3D system. So we need to solve for one continuity equation and 3 momentum conservation equations. So on the whole it becomes 4 partial differential equations. So answer is option B. 4 is the right answer. So it is one continuity equation and 3 momentum conservation equations. So x direction, y direction and z direction. Because we are dealing with problems in 3 dimension. The question itself it is clearly mentioned that for 3-dimensional incompressible flows, the minimum number of partial differential equations to be solved is. Because in the system where we are considering incompressible flows, there will not be much variation in the density, so we are not accounting for the energy change equation, energy conservation equation. So we have 4. If it is a compressible flows, it becomes 5. So we need to be clear in that. Now moving on to question 2. What do we got here? We got that which of the following is a characteristic feature of the artificial compressibility approach to solve incompressible Navier-Stokes equation. So I repeat, which of the following is a characteristic feature of the artificial compressibility approach to solving incompressible Navier-Stokes equation. So in solving for the incompressible Navier-Stokes equations, one of the methods is artificial compressibility approach. So in the question it is asked that which of the following is a characteristic feature. So we'll go one by one. So first one, it is mentioned pressure need not be evaluated. Pressure need not be evaluated. Second one, can be applied to unsteady flows. And third one, cannot be applied to 3-dimensional flows. So now what do we mean by artificial compressibility approach is that it is a method in which the solution is following a similar approach to the compressible flow systems. So here we are introducing an additional factor, so and artificially making the equations to behave such a way for the compressible flows so that we can solve the system. So in this what is the basic feature? So first one, pressure need not be evaluated. So this one is a true statement because we are since it is similar to compressibility equation, we are not evaluating for the pressure during the solution of the equation. So first one is true. And second one, can be applied to unsteady flows. So artificial compressibility approach actually mostly fits well for the steady flow systems. So it is not preferred for the unsteady flows. So second one is false. And third one, it is given cannot be applied to 3-dimensional flows. So again it is false because artificial compressibility approach can be applied to 3-dimensional flows. The only thing is it is similar to how we get the solution for the compressible flows. We are using it for the incompressible flows by introducing some additional factor. So the concept we will see in the next slide. But basically out of the three statements, first one is true, second one is false, and third one is false as well. So we will look at the options first. Option A 1, option B 2, option C 3, option D 1 and 3. So now we know that only first statement is the right statement, the second and third are false. So Option A is the right answer. That is option A, 1 is the right answer. So answer is option A, that is 1. That is, we need not evaluate for the pressure when we are using the artificial compressibility approach to solve for the incompressible Navier-Stokes equations. So now we will see what is artificial compressibility approach. So basically, when we are talking about incompressible flow system, what is the major issue is that we have continuity equations and we have momentum conservation equations. But in incompressible flow systems, we take density as constant, and therefore it is not present in the continuity equation. So if we remember continuity equation, for the general continuity equation, it will be like dou by dou x of rho u, dou by dou y of rho v plus dou by dou z of rho w equal to 0. But now since it is like rho is constant, the equation becomes del dot u equal to 0. We are not keeping density constant. Density is constant, so it is not varying. So only velocity is varying. So del dot u equal to constant is the equation, continuity equation for the incompressible flow systems. So in if we look at the continuity equation, there is no pressure or density in present in the system. Whereas in the momentum conservation equation, we have additional terms. So we cannot we cannot separate the continuity and the momentum conservation equations because those terms are not present in the continuity equation. So what happened is that Poisson equation is additionally solved in such cases for calculating the pressure field given a velocity field that satisfies the incompressibility condition both inside the computational domain as well as at the boundaries. So in order to tackle these things, what happened is that Koren in 1967 proposed a different approach called as artificial compressibility approach, that is AC, and he proposed this method in order to overcome the difficulty of the pressure decoupling. So in artificial compressibility method, what happens is that a fictitious time derivative of pressure is added to the continuity equation so that the set of equations modified from the incompressible Navier-Stokes equations can be solved implicitly by marching in pseudo time. So the main thing is in incompressible flow systems, we cannot decouple the continuity and momentum conservation equations very directly because in the continuity equations we have the absence of density. So in order to tackle this, what Koren in 1967 proposed is that he introduced a new fictitious time derivative of pressure in the continuity equation so that the system of equations get modified and we will be able to solve it implicitly by marching in time. So this method is known as artificial compressibility approach, and it is used in order to overcome the difficulty when we are dealing with the pressure decoupling. So mostly this artificial compressibility method is limited to steady flow system, and it can be used for the three-dimensional space as well. So it is not an issue. So how it is being used is that, as I mentioned, del dot u is the incompressible continuity equation. So as the name implies, that is, as the name artificial compressibility implies, an artificial linkage between the continuity and the momentum equations is created by introducing an additional term in the continuity equations as follows. So we were talking about how continuity equation doesn't have the term for pressure or density, and therefore it becomes difficult for the pressure velocity decoupling when we are dealing with incompressible flow systems. So he introduced an artificial linkage between the continuity equation and the momentum conservation equation by introducing one new term, and it is known as fictitious pressure fictitious time derivative of pressure. So this become dou rho by dou t plus del dot u equal to 0. Dou rho by dou t plus del dot u equal to 0, and this rho star is known as fictitious density, and it is linked to the pressure through a fictitious compressibility factor where rho star equal to P by beta square. So since it was difficult for the pressure velocity decoupling, what Koren in 1967 had done is that he introduced an additional time derivative of fictitious density, that is dou by dou t of rho star, in the original incompressible continuity equation. So it becomes dou by dou t of rho star plus del dot u equal to 0. So this is the new continuity equation, and here rho star is the fictitious density and it is linked to the pressure through the fictitious compressibility factor beta, where rho star equal to P by beta square. So additionally, how the equation turns out is that rho star is equal to P by beta square. So P r rho, okay, rho by beta square. So it becomes 1 by beta, just check with it, rho or P, but it here it is fine since we are dealing with only concepts. So 1 by beta square into dou rho by dou t plus del dot u equal to 0, and this is the momentum conservation equation, which is dou u by dou t plus del dot uu equal to minus 1 by rho del p plus mu by rho del square u. So this is the newly formed continuity equation wherein we are introducing the fictitious compressibility factor. So this factor is introduced over here, and this is the new continuity equation, and this is the momentum conservation equations. So these are the equations which we will be solving. So here we need not solve for the pressure. It can be evaluated using the known compressibility factor, and it does not generate a time accurate solution. It does not generate a time accurate solution. Therefore, it is limited to the steady state flow fields. So when it cannot generate a time accurate solution, it is better to apply for the steady state flow fields. So this is about the artificial compressibility approach. So in the question, if we go back, what was asked? Which of the following is a characteristic feature of the artificial compressibility approach to solving incompressible Navier-Stokes equation? So as we know now, we have three things. The answer is pressure need not be evaluated. Pressure need not be evaluated, and that is the answer, because artificial compressibility approach can be applied to steady state flows. It cannot be applied to unsteady flows, and similarly it can be applied to three-dimensional flows. So that is not an issue. So second and third statements are false statements, whereas the first statement is the true statement. So answer is option A, 1 is the right answer. Now we will go to question 3. So in question 3, it is about this staggered grid system. So we'll see the question first. In the question, what is asked is that which of the following variables are evaluated at the same location in staggered grid? Which of the following variables are evaluated at the same location in a staggered grid? So we will look at the options. First one, it is u velocity, that is x velocity, and second one it is v, that is y velocity, and third one it is pressure, and fourth one it is temperature. So what happens is that this is how calculation happens in the staggered grid. So here it is asked that which of the following variables will be evaluated at the same location. So we have u velocity, v velocity, and pressure and temperature. So if we look at, this is how calculations are being done in the staggered grid system, and velocities are calculated along the edges of the grids, whereas uh, scalar variables like pressure and temperature are calculated at the center of the cell. So if we take it, if we look at this particular figure, we can see that scalar variables will be calculated at the midpoint of the cells, middle of the cells, whereas the vectors like u and v will be calculated along the lines, along the edges of the grids. So this is how the calculation is being done in the staggered grid. So here if we take a look at this particular figure, we can see that x velocity is u. So u will be calculated at this point, at this point, at this point, and so on. Whereas y velocity is v, and it will be calculated at this point, this point, this point, and so on. Like those things, we will have evaluation for u velocity and v velocity. So u is being evaluated here, v is being evaluated here. So u and v are not exactly calculated at the same location in a staggered grid. Whereas if we take a look at pressure and temperature, we know that both of them will be evaluated at the midpoint of the cells. So these two are evaluated at the same location in a staggered grid, whereas u, that is x velocity, and y velocity v are being calculated at different location in the staggered grid system. So answer is option 3 and 4. So pressure and temperature, so these scalars are evaluated at the same location in a staggered grid, whereas the vectors u and v are calculated at different locations. So here u velocity and there v velocity, so those kind of things are being evaluated at different locations, whereas scalars like pressure and temperature are calculated at the same positions. So now let us look at the options first. Option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 3 and 4. Option D, it is 1 and 4. So now we know that we need to pick the right combination, wherein we will be saying that those two are evaluated at the same location in a staggered grid. So here we know that velocity vectors u and v are calculated at different locations, whereas the scalar variables like pressure and temperature are calculated at the same cell point, cell middle. So here 3 and 4 is the correct answer. So answer is option C. Option C is nothing but 3 and 4. So which of the following variables are evaluated at the same location in a staggered grid? So answer is option C, that is 3 and 4. So pressure and temperature scalars are evaluated at the same point, same location in a staggered grid system. So answer is option C is the right answer. Option C, that is 3 and 4 is the right answer. So this is how the staggered grid looks like, wherein the evaluation of pressure and velocity are scalars and vectors are being evaluated at different locations. So that is this thing. Now we will go to next problem. In question 4, what is being asked is that which of the following methods require an equation of state? Which of the following methods requires for an equation of state? Now we will look at the option first. Which of the following methods requires an equation of state? So first one, streamline vorticity method, and second one, artificial compressibility approach, and third one, McCormack method. So out of these three methods, two methods, that is stream function vorticity approach and artificial incompressibility approach, are being involved in the calculation of flow for the incompressible flow systems, Whereas the third scheme, that is McCormack scheme, is generally used for the compressible flow systems. So here the question is, which of the following methods requires an equation of state? So apart from the stream function, we should rule out the stream function vorticity method, and the answer to it is 2 and 3. That is artificial compressibility approach, and third one is McCormack method. Why? Because in artificial compressibility method we know that this method is similar to the compressibility flow method. So this method is similar to the compressibility flow method, and we have the need for the calculation of the pressure through the equation of state, similar to how we do it in the compressibility flow solution. So, and since McCormack method is again a compressibility flow scheme, we require the additional equation of state as well. So second as well as third method requires an equation of state for evaluation of pressure, temperature, so those things. So 2 and 3 is the right answer. And we look at the options. So option A 1, option B 2, option C 3, option D 2 and 3. So now we know that it is the right answer is option D, 2 and 3 is the right answer. Because similar to how we do it in the compressibility flow solution, we use the artificial compressibility approach and McCormack scheme to get the solution. So answer is option D, that is 2 and 3 is the right answer. Now we will see the answer, that is option D, 2 and 3. Now we will go to question 5. This is question 5. In question 5 we have one figure, and we will be the questions that follows will be based on this. So it is incompressible flow through a contraction in a pipe of circular cross section. And what question follows is that most of the following statements is or are correct about incompressible flows. So here we are given some statements, and we need to identify which of them are correct and which of them are wrong for incompressible flows. So the first one is that most gas flows are incompressible, and second one is that most of air can be incompressible if the flow speed is sufficiently high. So I would say that both the statements are first of all wrong. We will see how. The first statement, it is given that most gas flows are incompressible. So actually we know that in mostly, even though we say that gas is a compressible fluid, when we are talking about the flow condition, we are not talking about the fluid property, we are talking about the flow property. So for compressible flows of gas, we have the condition that Mach number should be greater than 0.3. If it is less than 0.3, we call it as incompressible flows. So we cannot generalize the statement as most gas flows are incompressible or compressible, because the gas flow equations depends on the Mach number, so it is false. Second statement, it is given that flow of air can be incompressible if the flow speed is sufficiently high. If speed is sufficiently high, it would most probably go under the compressible flow, not incompressible flow. So the second statement is false as well. So answer is option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So answer is both the statements are false statements. So answer is option D, that is neither 1 nor 2. Answer is option D is the right answer, because most of the following, most gas flows we cannot generalize as incompressibles, because it depends on the Mach number. Similarly, flow of air can be incompressible if the speed is very low, but otherwise it is compressible. So neither 1 nor 2 is the right answer. Now we will go to next question, that is question 6. Okay, we have a brief answer discussion over here. So question 5 itself. While all flows are compressible, flows are usually treated as being incompressible when the Mach number is smaller than 0.3. So here mostly all flows will be, ideally speaking, it can be compressible, and when it is less than a 0.3, the Mach number is less than 0.3, we call a flow as incompressible flows. So Mach number is nothing but the ratio of speed of the flow to the speed of sound in that particular medium. So next one, it is Mach number is actually defined by U by C, where U is the local flow velocity and C is the speed of sound in the medium. If velocity is high, Mach number will be large, therefore flow will be compressible. If velocity is low, Mach number will be low, so the flow can be incompressible. So that is it. Now we will go to question 6. In question 6, what is asked is that which of the following is or are among the difficulties encountered in the solution of incompressible flows? Which of the following is or are among the difficulties encountered in the solution of incompressible flows? So first one, it is coupled equations. Second one, non-linearity of governing equations. Third one, it is determination of pressure. So here two things are there. First is that we should see that what are all the difficulties encountered during the solution of incompressible flows. So first one, it is given that coupled equations. So as we know that in momentum conservation equation, we have the variables like velocity as well as pressure in the three equations, and it is therefore mostly the equations are known as pressure velocity coupling, pressure coupled equations, and the equations are non-linear as well. So that we have seen in the last class itself, how the equations are known as coupled equation and the non-linear equation. So here it is like non-linear because we have one term in the momentum conservation equation, that is u dot delta u. So if we remember the momentum conservation equation in the generalized form, it is like dou u by dou t plus u dot delta u equal to nu into del square u plus g, rho g or some g. So here it is in the left hand side, what have we got? We have got the variation term, that is dou u by dou t. Along with that we have u dot delta u. So this particular term is like velocity vector is multiplied by its own gradient. So it accounts for the non-linearity in the system. Similarly, we have pressure as well as velocity presence in these equations. So it accounts for the coupled equation as well. So first one coupled equation and second one non-linearity of the governing equations. Both of these make the solution to be very difficult in obtaining. And third one, it is given the determination of pressure. While it was easier for the pressure to be determined in the compressible flows, because once we get the solution from the continuity equation and the momentum conservation equation and the energy balance equation, we will get the solution, and on using that solution we can get the value of pressure from the equations of state. So that was how it was done in the compressible flows. But when we are talking about incompressible flows, determination of pressure is again a difficulty. Why? Because in the continuity equation, if it gets simplified by means of introducing that density is constant, we will get the equation as del dot U equal to 0. So it is an issue between the continuity equation and the momentum conservation equations, because here in the momentum conservation equations we have terms for pressure, density and velocity, whereas in the continuity equation we have only velocity values. So determination of pressure is again a difficulty when we are talking about incompressible flow systems. So coupled equation, nonlinearity of governing equation and determination of pressure, all three of them are a difficulty encountered in the solution of incompressible flows. So now we will first look at the option and we will talk about the answer as well. So option A, it is 1 and 2. Option B, it is 2 and 3. Option C, it is 1 and 3. Option D, it is 1, 2 and 3. So which of the following is among the difficulties encountered in the solution of incompressible flows? So first one, coupled equation, second one, nonlinearity of governing equations, and third one, determination of pressure. So now we are very sure that option D is the right answer, because all of them are difficulty encountered in the solution of incompressible flows, because the equation is a coupled equation and it is nonlinear governing equations. Nonlinearity is present in the governing equation. And also when we are talking about pressure, its evaluation is quite tricky for the incompressible flows, whereas evaluation of pressure was easy for the compressible flow systems. So for this case, all three are the difficulties encountered. So the answer is option D. That is option D, 1, 2 and 3 is the right answer. So that is for question 6. Now we will go to our next question. Our next question is on, okay, we got it, simple explanation. Continuity equation has dou u by dou x plus dou v by dou y equal to 0. I am writing it in the two-dimensional form. And momentum balance equation in the x direction is dou u by dou t plus dou u square by dou x plus dou u v by dou x equal to minus 1 by rho dou p by dou x plus mu by rho dou square u by dou x square plus dou square u by dou z square. Sorry, dou u square u by dou y square. So here the density will be present in these terms. However, since it is a constant, we have removed and taken it to the other side. And we have one more momentum balance equation in the y direction. When we are talking about two-dimensional system, we will have two momentum balance equation. And that momentum balance equation in y direction is given by dou v by dou t plus dou by dou x of, okay, here rho won't come. So here it is dou v by dou t plus dou by dou x of uv plus dou by dou y of rho v, dou by dou y of v square equal to minus 1 by rho dou p by dou y plus mu by rho dou square v by dou x square plus dou square v by dou y square. So here I am talking about these terms. Here it is like a nonlinear system, and also we have pressure variable and velocity variable in a single equation. So therefore coupled equation. So again it is difficult. And when we are talking about incompressible flows, rho is absent in the continuity equation. So it is difficult to decouple between these equations when we are using incompressible flow systems. So all three statements were leading to difficulty encountered in the incompressible flow systems. So that is question 6. Now we are moving to question 7 actually. In question 7 again the same figure is there, where incompressible flow through contraction in a pipe of circular cross section. So this is a circular cross sectional pipe, and we have incompressible flow through the system wherein it is reducing its cross-sectional area and it is contracting the flow. Now we will see what question is about. Consider the steady incompressible flow through the contraction section of the circular pipe shown schematically in figure 8.1. For this flow, which of the following can be neglected? So the question is very simple. Here it is asked that consider the flow, and here the flow is a steady state flow and it is an incompressible flow through the contraction section. So here it is contraction section in the circular pipe as shown schematically in figure 8.1. For this flow, which of the following can be neglected? So options are option A. Okay, we have two things. First one, it is pressure variation in the flow direction, and second one, it is density variation in the flow direction. So now in the question, it is clearly asked about the incompressible flow. So the flow is a steady flow and the flow is an incompressible flow through the contraction section of the circular pipe shown in 8.1. So for this flow, which of the following can be neglected? So we are given pressure variation in the flow direction and density variation in the flow direction. So here if we look at it, when we are talking about incompressible flows, we all know that there is no major density change across the pipe. So this is the case when we are talking about the incompressible flows. I am not talking about compressible flows. In compressible flows, density variation will be there, especially when we are talking about the contracting section of the circular pipe, whereas the density variation is less for the even though it is in the contracting section of the circular pipe, but the flow is the incompressible flow. So density variation can be neglected, whereas pressure variation we cannot neglect because pressure will be high at one point and at the other end it will be very low. So pressure driven flows, so those things are there, so we cannot neglect the pressure variation in the flow direction. So this is answer is option 2. Second one is the right answer because we can neglect the density variation, whereas we cannot neglect the pressure variation. So we will look at options first. Option A 1, option B 2, option C 1 and 2, option D neither 1 nor 2. So the answer is actually option 2, that is density variation in the flow direction can be neglected, and it is rightly given from option B. B2 is the right answer. Now again we are going to question 8, and in question 8 we have a problem from the same figure, and what is being asked is that incompressible flow through a contraction in a pipe of circular cross section. Same figure. Now we will read the question. If the flow in figure 8.1 is unsteady, axisymmetric and viscous, then how many partial differential equations need to be solved to get the flow field? So I repeat the question. It is very straightforward question. You people can also answer it. So here we are talking about a flow through the incompressible flow through the contraction in a pipe, and it has circular cross section. So the flow is described as unsteady, axisymmetric and viscous flow. So now how many partial differential equations we need to solve? This problem is similar to one problem that we saw in last class. So I'll give you a hint. It is related to the word axisymmetric as well. Okay, we'll discuss the answer. So now it is an incompressible flow. So we need not solve for the energy balance equation, but remaining equations we need to solve. Of that we have one continuity equation, and if we talk about momentum conservation equation, we will have in the x, y and z direction. Because the pipe is given as circular cross section, we will be having 3 dimension. But if we look at the question statement, it is clearly given that flow is axis symmetric. So we can solve for 2 axes only. So one dimensional we can neglect. Therefore, momentum conservation equation becomes 2 equations. We can neglect one equation because the flow is axis symmetric. We will look at the options now. Option A, it is 5. Option B, it is 4. Option C, it is 3. Option D, it is 2. I'll repeat once again. Whenever we are talking about incompressible flow systems, the main equations that we need to solve is continuity equation and 3 momentum conservation equation. And unless there is any external energy transfer happening, we need not solve for the energy conservation equation, because in compressible flow systems the density variation was observed, so we solve for the energy conservation equation as well. But that is not the case here, so we can neglect that. So let us consider this flow is a purely cold flow system where it is flows through the contracting section, and flow is unsteady flow and axis symmetric flow and viscous flow. So here the flow is given as axis symmetric, so instead of 3 dimensions it is sufficient to solve for the 2 dimensions. So the number of equation becomes 1 continuity equation and 2 momentum conservation equations. So on the whole it becomes 3. So answer is option C is the right answer. That is 1 continuity equation and 1 x momentum and 1 y momentum, or like 2 momentum conservation equations. So that was for question 8. Now we will look at question 9. In the question 9, again we are dealing with the same figure where the flow is incompressible flow through a contraction in a pipe of circular cross section. And we have 3 statements actually. Of the 3 statements, we need to identify which of the statements is true. Okay. So I'll read the question first. In question, what is asked? For the steady axisymmetric incompressible laminar flow case shown in 8.1, which of the following statements is true about the stream function vorticity method? So here we are now moving on to stream function vorticity method, and again in the question it is mentioned that it is a steady state problem, axisymmetric problem, and incompressible problem, and laminar flow problem. So here this is the figure wherein the flow is through the contraction section in a pipe of circular cross section, and we are talking about the statements are about when we use the stream function vorticity approach. So here we will read the statements one by one and see whether they are true or false. In the first statement, it is given that it cannot be used because the flow is laminar, and we know that statement is false because in nowhere it is mentioned that stream function vorticity method should only be used when we are talking about laminar flow or turbulent flow. So stream function vorticity method can be used for this case actually. So first statement is false. Second statement, it is given that it cannot be used because the flow is 3D. Again, this is the false statement. Why? Because even though stream function vorticity method is restricted to the two-dimensional case, in the statement it is clearly given that for the steady axisymmetric incompressible flows. So since it is an axisymmetric problem, even though the original system under our consideration is a circular cross-sectional pipe, it reduces to two dimensions that we already saw in the last slide. So it can be used. The stream function vorticity method can now be used for the solution. So second is false as well. As for the third statement is concerned, it cannot be used because the method can be used only for Cartesian coordinate system. So again, this statement is a false statement. So it is stream function vorticity method is mostly a two-dimensional approach, and wherein we are introducing two variables, stream function and vorticity, and replacing the original variables in the system of equations and getting the solution. So here all the three statements are basically false. Why? Because first statement is mentioning that it cannot be used because the flow is laminar. That is a false statement. And second statement is also true because here we are dealing with an axisymmetric system, therefore we can use the stream function vorticity approach. And third one is it cannot be used because the system can be used for Cartesian coordinates only, and that is again a false statement. So coming to the options, we will see that option A 1, option B 2, option C 3, option D none of the three is correct. So we know that option D is the right answer. That is none of the three is correct is the right answer, because all the given statements are false statements only. Now we will go to question 10. Okay, answer is option D. None of the three is correct. Now we will go to question 10. Okay, question 9 we have a simple thing. So it is about stream function vorticity approach. In stream function vorticity approach, it is a way to deal with the difficulty that pressure appears in the momentum equations but not in the continuity equations for incompressible flows, has been to eliminate pressure from the momentum equation. So as we have already seen that when we are talking about incompressible flow systems, density becomes constant, so therefore we are taking rho as constant, so it disappears from the continuity equation, whereas it is still present in the momentum conservation equations. So since it is present in one equation and absent in the other equations, it is difficult to get the solution for the pressure. So one way to deal with that was artificial compressibility approach, wherein we introduced one variable in the continuity equation as rho star. So the next method is that to eliminate pressure from the momentum equation. So major issue is that in the second equation, momentum conservation equation, we have the pressure term, but the way here in stream function vorticity approach is that we are eliminating the pressure from the momentum equation. For two-dimensional flows, this is possible by the introduction of new variable called stream function, and it is lines of constant stream functions values are the streamlines. So which enables the three coupled equations involving u, v and p to be written as two coupled equations involving stream function and vorticity and one decoupled Poisson equation for pressure. And unlike the artificial compressibility method, this approach can be used to generate time accurate solutions but only for two-dimensional flows. So here I'll give you one quick thing. Here there are two ways till now. Till now we have seen two ways to deal with the solution of incompressible flows. One way was to use artificial compressibility approach, and the second one now we have seen is stream function vorticity approach. What happens is the artificial compressibility approach. In artificial compressibility approach, we introduce an additional rho star fictitious term, time derivative of the fictitious term in the continuity equation. whereas here we are eliminating the pressure term from the momentum conservation equation, and therefore we are getting and we are solving it by introducing a new variable stream function, and the three coupled equations now becomes two coupled equations involving stream function and vorticity, and one decoupled Poisson equation for pressure. So in artificial compressibility approach, it was used to generate for the steady state solutions, whereas this method can be used for used to generate time accurate solutions, but one limitation is that it can be used for the two dimensions only. So therefore for 2D incompressible flows, it is possible to recast the Navier-Stokes equation in an alternative form in terms of the stream function and the vorticity. So for 2D systems, what we are doing, we are just recasting the Navier-Stokes equations in alternate form by using the stream function and the vorticity variables. And in many applications, the stream function vorticity form of the Navier-Stokes equations provides better insight into the physical domains driving the flow than the primitive variable formulation in terms of U, V and pressure. The stream function and vorticity approach is also useful for numerical work since it avoids some problems resulting from the discretization of the continuity equation. So what we are saying is that this particular method, that is the stream function vorticity method, is as we have seen that we are just recasting the equation, Navier-Stokes equation in another form by using these two variables, that is stream function and the vorticity, and this is applicable for two-dimensional systems only. But in many of the applications, this form of the Navier-Stokes equation involving stream function and vorticity was found to provide better insights into physical mechanisms than the original way in terms of using U, V and pressure equation. And this formulation is also useful for numerical work. So since it avoids problems resulting from the discretization of the continuity equation. So this is, although it is applicable to two-dimensional system, it has its own advantages as well. So when we talk about the question, it was like none of the three is correct because it cannot be used because the flow is laminar is a false statement. Similarly, it cannot be used because the flow is 3D. Even though the statement is a generalized true statement, in context to figure 8.1, we are saying that it is for a steady axisymmetric incompressible laminar flow. So this is false. Like stream function vorticity approach can be used for the laminar flow, and stream function vorticity approach can be used for the this system, because here even though the system is 3D, we are considering the axisymmetric assumption, so we can use, and it can be used for this system of for this coordinate system as well. So now that is for question 9. We will go to question 10 now. In question 10, what is being asked is that for the steady axisymmetric incompressible laminar flow case shown in figure 8.1, which of the following statements is true about the artificial compressibility method? So again, now we are talking about the artificial compressibility method. In the previous question, it was about stream function vorticity method. Now we are talking about artificial compressibility method. So the flow is similarly to the steady axisymmetric incompressible flow through this particular contraction section in a pipe of circular cross section. So what are all the three statements given? First one, that it cannot be used because the flow is laminar. Second one, it cannot be used because the flow is 3D. Third one, it cannot be used because the flow is steady. So when we talk about artificial compressibility method, what happens is that we are introducing a new additional term, that is time derivative of the fictitious density, that is rho by dou t of rho star in the continuity equation. So this additional term is derived from the compressibility factor beta, where beta equal to rho by rho star. something like that. So beta equal, sorry, P star by P, P rho star by rho, something like that. So we are getting it from the compressibility factor. So that is how we are getting the one more fictitious term. So when we talk about these statements, the first one, it is mentioning that it cannot be used because the flow is laminar. So even though the flow is laminar, here we can use the artificial compressibility method. So first statement is true. Second one, it cannot be used because the flow is 3D. The flow is first of all axisymmetric flow, but even if it is 3D or not, 3D artificial compressibility method can be used. So that is not an issue. And third statement, again it is mentioning that it cannot be used because the flow is steady. Artificial compressibility method is mostly preferred for the steady flow systems only, not for the unsteady flow systems. So this statement is false as well. So option, okay, all three statements are false. Now when we look at the options, option A it is 1, option B it is 2, option C it is 3, option D it is none of the 3 is correct. The answer is actually option D, none of the 3 is correct is the right answer. Option D. So now we'll just I am just checking for that fictitious term actually. I think it was question 4 maybe. Okay, here. So as the name implies, an artificial linkage between continuity and the momentum equation is created in the artificial compressibility method by introducing the new term in the continuity equation. So this is dou rho star by dou t plus del dot u equal to 0. Ideally, del dot u equal to 0 is the continuity equation for the incompressible flows. But now we are introducing a new term, that is rho star, dou rho star by dou t. And rho star is fictitious density. It is linked to the pressure through a fictitious compressibility factor, where beta equal to rho star equal to p by beta square, and we get 1 by beta square into dou p by dou t. It is dou p by dou t. So if it is rho, it is rho both the place. If it is p, it is p both the place. If you have any doubts, I just request you guys to check it. So this is how we do it in the artificial compressibility approach, wherein we are introducing the additional fictitious density term in the continuity equation, and therefore providing a linkage between the continuity equation and the momentum conservation equation. So now the pressure can be evaluated using the compressibility factor, and it does not generate a time accurate solution. Therefore it can be applied only for the steady state problems. So these are the things for the artificial compressibility approach. So from that itself, we are now clear that when we are talking about artificial compressibility method, it can be used for the laminar system and it can be used for three-dimensional system, even though the system here is solved for the 2 dimensions only, because it is axisymmetric system, and it cannot be used, it can be used for the steady state. It cannot be used for the unsteady state. If that is the case, this is a true statement, but it can it can be used for the steady state problems. So answer is again none of the three is the right answer. Option D is the right answer. Now we are going to question 11. In question 11 we are again seeing the flow through a contraction in a pipe of circular cross section, and we are asked that which of the following methods can be used for the flow shown in figure 8.1. So this is figure 8.1. So which of the following methods can be used? First one, it is McCormack method. Second one, it is pressure equation method. And third one, it is pressure correction method. So here in figure 8.1, what sort of flows we have? We have incompressible flows. So what method can be used? We can use pressure equation approach and pressure correction approach as well. Whereas the McCormack method given in statement 1, it is an approach used for the compressible flow systems. So in the question it is asked about incompressible flow through a contraction in a pipe of circular cross section. So first one is false, whereas 2 and 3 are correct. Pressure equation approach and pressure correction approach. Both 2 and 3 are right. First one is false. So options are A 1 and 2, B 2 and 3, C 1 and 3, D 1, 2 and 3. So which of the following methods can be used for the flow shown in figure 8.1? So first one, it is McCormack method. Second one, it is pressure correction approach. Third one, it is second one pressure equation approach. Third one, it is pressure correction approach. So answer is option option B, that is 2 and 3 is the right answer. So answer is option B, because McCormack method is a method for the compressible flow systems, whereas 2 and 3 are for the incompressible flow systems. So McCormack scheme and beam warming scheme are for the compressible flow schemes, and for incompressible flow schemes we have stream function vorticity approach, artificial compressibility approach, pressure correction approach, and pressure equation approach. So 4 approaches for the incompressible flow systems we have studied. So answer is option B. 2 and 3 is the right answer. Answer is option B. 2 and 3. And here we got methods for solving incompressible fluid flow are, first one, it is artificial compressibility method. Second one, it is stream function vorticity method. And third one is pressure equation approach. And fourth one, it is pressure correction approach. So these are the 4 methods for solving incompressible fluid flow problems. Incompressible flow problems. So now we have seen question 11. Now we will see for question 12. In question 12, it is given that the pressure correction approach cannot be used for dash. Pressure correction approach cannot be used for dash. Option A, time dependent flows. Option B, 3-dimensional flows. Option C, viscous flows. Option D, none of the above. So here again we are asked about when to use pressure correction and when it cannot be used. So if we see that option A, it is time dependent flows. Okay, option A, time dependent flows. Option B, 3-dimensional flows. Option C, viscous flows. Option D, none of the above. So actually pressure correction approach can be used for 3-dimensional flows. It can be used for time dependent flows, and it can be used for viscous flows as well. So all 3 are the cases where pressure correction approach can be used. whereas there is nothing here which states that it cannot be used for that case. So answer is option D, none of the above. Option D, none of the above is the right answer. How? Because pressure correction method is a class of methods that is used in computational fluid dynamics for numerically solving the Navier-Stokes equations, normally for incompressible flows. So it is a class of methods used in CFD for mostly solving the Navier-Stokes equations for the incompressible flow systems. So there are series of steps involved in pressure correction approach, and I'm just giving it here for your reference, not for anything else. First, what we do is we have an initial guess values for pressure P star, U star and V star, and later we solve the discretized x momentum equation for U star, and similarly we solve discretized y momentum equation for V star, and for pressure correction equation, we solve the pressure correction equation to get P dash, and from P dash we calculate the velocity corrections. Apart from P dash we calculate the velocity corrections U dash and V dash, and we calculate other scalars involved in the system, and after obtaining the correction variables, we update the P, U, V and return to the first steps if it is not converged. So what we do is that we initially have some guess values for P star, U star and V star, and from that we get the discretized x momentum equation and solve it, and obtain values for U star and solve discretized y momentum equation and obtain V star, and also we get the pressure correction term P dash. So after P dash we get the U dash and V dash, that is velocity correction terms, and after that we obtain other scalars, and from all the variables, like we have the guess values and also we got the correction values. So we update P, U and V, and we return to the first step, like if it does not converge, or we go with the solution. So this is the pressure correction method. It is a class of method used in the CFD to get the solution for the Navier-Stokes equations when we are dealing with the incompressible flows, and these are the steps used over there. So it can be used for the three-dimensional flows, it can be used for time dependent flows, it can be used for viscous flows. So all three it can be used. So option D, none of the above is the answer, because in the question it is asked that pressure correction approach cannot be used for, it cannot be used for. So answer is option D, none of the above. So now we will go to question 13. In question 13, what is asked is that the full form of the simple method is dash. So simple is one of the solver. We use it in CFD to get the solution. And what is the full form of the simple? Like we all seen that we use simple algorithm. So what exactly is the full form of the simple is? So options are option A, steady implicit method for pressure linked equation. Option B, scheme for incompressible pressure linearized equations. Option C, steady incompressible method for pressure linked equation. Option D, none of the above. So we have three options. The first one, it is given steady implicit method for pressure linked equation. Second one, it is given scheme for incompressible pressure linearized equation. And last, it is given steady incompressible method for pressure linked equation. So actual full form of simple is semi implicit method for pressure linked equations. So it is actually none of the above is the right answer. Option D, none of the above is the right answer. Why? Because simple full form is semi-implicit method for pressure linked equation. Semi-implicit method for pressure linked equation. So this is the full form, and it is not given in any of the options. So answer is none of the above. So I hope it is clear now. Now we will go to next question. Question 14. In question 14, what is asked is that a staggered grid system is used dash. A staggered grid is used dash. Staggered grid system we have seen in one more problem as well, where velocity was calculated at the grid lines, that is edge lines, and midpoint of the edge lines, and scalars are calculated at the center of the cells. So a staggered grid system is used dash. So that was how it was implemented. Now we are talking about it is used when it is used. So option A, to enable treatment of flow domain of irregular shapes. Option B, to simplify grid generation. Option C, to eliminate checkerboard oscillations in pressure. Option D, to overcome the stability problem. A staggered grid system is used to enable treatment of flow domain of irregular shape. Option B, to simplify grid generation. Option C, to eliminate checkerboard oscillations in pressure. Option D, to overcome the stability problem. So when we are talking about staggered grid systems, why do we use it? We are using it to eliminate the checkerboard oscillations in pressure, because it gives rise to some negative and not negative, zero values and high values when when we were calculating for the pressure. So it was not ideally suitable to calculate it all at the same points, pressure and velocity at the same points. So staggered grid system was used to eliminate the checkerboard oscillations in pressure. So answer is option C is the right answer. Option C, to eliminate checkerboard oscillations in pressure. So in CFD and numerical methods, a staggered grid defines variables like pressure and velocity at different positions on the grid, typically with pressure at the cell centers and velocity component at cell faces, to avoid certain numerical issues and improve stability. So it is a type of spatial discretization where the variables are not exactly defined at the same location, wherein we are defining it at different locations. So in collocated grid, all variables are at the same locations, but in staggered grid, we use different locations to define pressure and velocity. So pressure mostly it is at the cell centers or grid centers, and velocity is mostly at the centers of the cell faces or edges to which they are normal. So actually what it does is that it helps prevents spurious oscillations which can occur when we use when we use the same location for the pressure and velocity. So this also leads to more improved solutions. It is used in the incompressible flow systems only, so we'll see that. But one issue is that it is bit complex to implement and manage than the normal collocated grid. So what happens is that staggered grids are primarily used to avoid checkerboard oscillations in pressure fields, which can occur when using collocated grids for incompressible flow simulations. By storing velocity components at cell faces and pressure at cell centers, staggered grids effectively couple pressure and velocity, eliminating these oscillations and improve the accuracy of the solution. So that is the case. A staggered grid system is used to eliminate checkerboard oscillations in pressure. So this is the staggered grid, wherein we are able to see that we are calculating the pressure at cell centers and velocity at the cell faces or cell edges, midpoint of these. And for non-staggered grid, we are able to see that all the calculations are taking place at the same point, same grid points we use for calculating pressure as well as the velocity. So this image is taken from this particular paper, and I have given location as well. If you want, you can access it. So that is for question 14. In question 15, next we have that one figure. Previously we have seen about contraction section in the pipe flow. Now this particular figure is about diverging section, expansion section in the pipe flow. So what is being asked? Mostly it would be like similar questions being asked here. Consider the flow situation shown in figure 1. For which of the cases below will the flow likely to be incompressible? Okay, almost similar question to what we saw previously. So consider the flow situation shown in figure 1. So this is figure 1, and for which of the cases below will the flow likely to be incompressible? Option 1, it is when the gas flow through is nearly inviscid. Second one, when gas flow velocity is extremely high. So when do we say flow as incompressible? By now we know that we call the flow as incompressible when Mach number is less than 0.3. Mach number is defined as the ratio of velocity of fluid to the velocity of sound in the medium. So if it is less than 0.3, what it means is that velocity of fluid is low. So first statement is stating that when gas flow is nearly inviscid, so inviscid flow here has nothing to do with the incompressible flows. So first statement is false. Second statement, it is stating that when gas flow is extremely high. So normally we have seen that when gas flow is extremely high, it will exceed Mach number 0.3, so it becomes compressible flows. Also we have seen that if Mach number is less than 1, it is subsonic. If it is equal to 1, it is sonic flows, and if it is greater than 1, supersonic flows. So for supersonic flows, we need additional shock capturing techniques and all, so that we have seen in the last class. But coming back to the incompressible flows, we have velocity should be very low. So none of the two statements are correct actually. Both the statements are false. So here it is asked, for which of the cases below will the flow likely to be incompressible? So both are false only. So option A, 1 only. Option B, 2 only. Option C, 1 and 2. Option D, neither 1 nor 2. So now we know that both the statements are false. So answer is option D, that is neither 1 nor 2 is the right answer. Option D is the right answer. Now we will go to question 16. In question 16 again we have the same figure of incompressible flow through a diverging section expansion. Looking at the question, we have, you wish to compute the velocity and pressure variation for the flow situation in figure 1. So we wish to compute the velocity and pressure variation for the flow situation in figure 1. The flow is two-dimensional. Upstream and downstream ducts are extended on both sides of the expansion just as shown in the figure. Which of the following statements is wrong? So what do we got here? We have that you wish to solve the velocity and pressure variation for the flow situation in figure 1. So this is figure 1, and flow is two-dimensional flows. Okay, and upstream ducts and downstream ducts are extended in both the sides of expansion. So both the sides of the expansion joints, we have it extended as shown in this particular figure. So now we are asked to identify which of the statements is wrong. So we need to identify the wrong statement. So previously we have been seeing which is right. Now we are identifying a wrong statement. So first one is that the inlet velocity profile will not have any bearing on the flow in the expansion, and therefore it can be taken as uniform. The inlet velocity profile will not have any bearing on the flow in the expansion, and therefore it can be taken as uniform. Second one, the outlet velocity profile will not have any bearing on the flow, and therefore it can be taken as uniform. So we have two statements. So we need to identify the wrong statements. So we will see that. First one, it is given that inlet velocity profile will not have any bearing on the flow in the expansion. So it can be taken as uniform. So this is like fluid is coming from here and it is expanding. So it is like an extended section as well, and this has the inlet velocity is in no way being impacted because of the expansion. So whatever water is coming, it is coming, but this particular expansion joint is not creating any impact on the inlet flow side, inlet velocity. So inlet velocity profile will remain the same, and therefore it can be taken as a uniform. So first statement is actually true statement. Inlet velocity profile will not have any bearing on the flow in the expansion, and therefore it can be taken as uniform. The second statement, it is given that outlet velocity profile will not have any bearing on the flow, and therefore it can be taken as uniform. This particular statement is false. This statement is false because outlet velocity profile will have impact or will have impact because fluid is coming and it is expanded, and after that the outlet section is there. So outlet will definitely have some bearing on the flow, like velocity profile will be impacted by the expansion, so it cannot be taken as uniform. So second statement is false statement. So for this question, second statement is the right statement. Option 2 is the right one. Option A 1, B 2, C 3, C 1 and 2, D neither 1 nor 2. So we are given two statements, and of that we are asked to identify the wrong statement. Answer is option 2, that is the outlet velocity profile will not have any bearing on the flow, and therefore it can be taken as uniform. So that statement is the wrong statement. Why? Because the outlet section is after the expansion, so it will definitely have some impact, and therefore we cannot take it as an uniform. So option 2 is the answer. Option B, B2 is the right answer. Now we will go to question 17. Again in question 17 we are dealing with the diverging section expansion, and the flow is incompressible flow. If the flow in figure 1 is steady, viscous, two-dimensional and involves external heat transfer, how many partial differential equation needs to be solved? So what are the things given? The flow is steady flow, flow is viscous flow, flow is a two-dimensional flow, and it involves external heat transfer. So how many PDEs do we need to solve? So first we'll see. Flow is incompressible flows. So in general, what equations do we solve? In general, we solve for the continuity equation and momentum conservation equations when there is a cold flow involved. So we have one continuity equation, and if system is 3D, we have 3 momentum conservation equation. If it is 2D, we have 2 momentum conservation equation. So here in the question, flow is steady, viscous, two-dimensional and involves external heat transfer. So flow is steady, viscous, two-dimensional flow. So it is a two momentum conservation equation, one continuity equations, and it is mentioned that it involves external heat transfer. So we are heating it or we are cooling it, whatever, but it involves external heat transfer. So we need to solve for the energy conservation equation as well. So we have one continuity equation, two momentum conservation equation, and one energy conservation equation. So on the whole, we got four partial differential equations that we need to solve. So looking at options, we have option A 5, option B 4, option C 3, option D 2. So answer is option B 4 is the right. Option B 4 is the right answer. B4 is the right answer because we have one continuity equation, two momentum conservation equation, and one energy conservation equation. So we got four equations to solve. So now we go to question 18. Again, we are involving the flow in this particular section of diverging section flow, and we have a question that goes something like, if flow in figure 1 is isothermal, steady, viscous, two-dimensional, which of the following statements is true about using the stream function vorticity method? If flow in figure 1 is isothermal, steady, viscous, two-dimensional, which of the following statements is true about using stream function vorticity method? We'll look at the options. Option 1, statement 1, it cannot be used because the flow is laminar. Second one, it cannot be used because the geometry cannot be fitted in a rectangular grid. Third one, it cannot be used because the boundary condition for the stream function on the wall is not unique. So now we are talking about stream function vorticity approach. And we know that how we are replacing variables using stream function and vorticity and getting two equations for getting the solution of incompressible flow using Navier-Stokes equation. So in the figure it is flow is isothermal flow, steady flow, viscous flow, two-dimensional flow. So we got four things, and stream function vorticity method will be used only for the two-dimensional system. So that check is complete because it is mentioned in the question that the flow in figure 1 is incompressible and two-dimensional flow. So stream function vorticity method can be used. So now we need to identify if any statements are true. First one, it cannot be used because flow is laminar. So this is a kind of false statement because stream function vorticity method can be used even though the flow is laminar. Second one, it cannot be used because the geometry cannot be fitted in a rectangular grid. Again, this is false because geometry can be fitted in a rectangular grid because it is a two-dimensional system. It cannot be used because the boundary condition for the stream function on the wall is not unique. Again, this is kind of false. So all three statements are basically false statements. If we look at the options, option A 1, option B 2, option C 3, option D none of the three is correct. So the right answer to this problem is option D, none of the three is correct. Now we will go to question 19. In question 19, what is asked? The pressure correction approach can be used for which of the following? Pressure correction approach can be used for which of the following? Options are, okay, we have 1. Time dependent flows, 2. Three-dimensional flows, 3. Viscous flows. Okay, the same question was asked in the previous figure problem as it cannot be used for which of the following. Now we know that it can be used for all three because pressure correction approach can be used for time dependent problems and three-dimensional problems and viscous flow problem as well. So it can be used for all of these. Now we will look at options once. Option A 1 and 2. Option B 2 and 3. Option C 1 and 3. Option D 1, 2 and 3. So answer is option D 1, 2 and 3 is the right answer. Now coming to question 20, we have that which of the following is true in incompressible flow? Okay, for this answer is option D 1, 2 and 3 is the right answer because it can be used for all of these. Now coming to question 20, we have which of the following is true in incompressible flows? First one, velocity does not vary. Second one, pressure does not vary. Okay, we have two statements. First one, velocity does not vary. Second one, pressure does not vary. So we are asked which of the following is true when we are dealing with incompressible flows. Let us now consider flow through a cylindrical pipe. So we are passing fluid at some 5 meter per second at one end and it is reaching the other end. So here what will happen? Here it is like a pressure driven flow. Mostly when we are not passing anything, it is a pressure driven flow. So here pressure will decrease from one end to other end, and when we are talking about velocity, again the velocity will be varying. So we cannot say that pressure and velocity will remain the constant, right? Both of them will be varying. Velocity will be developing in a pipe flow where we will see that parabolic profile that remains steady after it reaching steady state, but till then velocity will vary, pressure will vary as well. So which of the following is true when we are talking about incompressible flow? We cannot generalize any statement as such. This particular example which we have seen about flow in a pipe, circular pipe, itself says that velocity and pressure does not remain constant. So both of them are false. So which of the following is true in incompressible flow? Velocity does not vary. 2. Pressure does not vary. So answer is both 1 and 2 is the right answer. Both 1 and 2 are false. So answer should be none of the above. Not both of them are false. They are not true. So option A 1 only. Option B 2 only. Option C 1 and 2. Option D neither 1 nor 2. So answer is option D, neither 1 nor 2 is the right answer. 20D is the right answer. we are going to question 21. In question 21, what we have got is that which of the following effects poses special problems in incompressible flows compared to compressible flows? So what are all the problems in incompressible flows compared to compressible flows? First one, non-linearity. Second one, coupling. So first one, in the question it is clearly asking that which of the following effects poses special problems in incompressible flows compared to compressible flows. So the problem should be present in incompressible flows, but it should be absent in compressible flows. So the non-linearity of the governing equations and the coupling involved in them, both of them are present in incompressible flows as well as they are present in compressible flows. So they are not any special problems only in the incompressible flows. So we cannot say that nonlinearity or coupling is only involved with the incompressible flows, because they are both involved in incompressible flows and in compressible flows. They arise from the governing equation in such a way that we have divergence, convective term that accounts for nonlinearity. So we have u dot delta u in the momentum conservation equation that accounts for the nonlinearity. Similarly, we have pressure and velocity in the governing equation, momentum conservation equation, that accounts for the coupling effects. So the nonlinearity and coupling is present both in incompressible flows and in compressible flows. So there is no special problem in incompressible flow than compared to compressible flows from the options given. So both of them are false. There is one more special problem in incompressible flows compared to compressible flows, that is the evaluation of pressure. Evaluation of pressure is difficult when we are dealing with incompressible flows, because when we are talking about compressible flows, pressure evaluation is very much easier. So the pressure evaluation is easier in compressible flows because we get pressure from the equation of state. So that is not the case in incompressible flows. So that is a special effect, but since it is not given over here, both of them are false. So options are A, 1 only, B, 2 only, C, both 1 and 2, D, neither 1 nor 2. So the right answer is option D, that is neither 1 nor 2 is the right answer. Now coming to problems come in the evaluation of pressure. Problems come in the evaluation of pressure. So this is for question 21. Now coming to question 22, that is the last question for today's session. Okay. Which of the following is false about pressure in incompressible flows? Which of the following is false about pressure in incompressible flows? Options are: option 1, it serves to enforce continuity constraint. Second one, it can be specified as a constant. So first one, it serves to enforce continuity constraint, that is true about pressure in incompressible flows, whereas second one, it can be specified as a constant, is false, because pressure is not constant in incompressible flows. Any flow involving incompressible flows, we are able to see that pressure is very much involved and we cannot assume it as a constant. So second one is false. Options are option A 1, option B 1 and 2, option C 2, option D none of the above. So which of the following is false about pressure in incompressible flows? So answer is option first one is true, second one is false. So answer is option C, that is 2. C2 is the right answer. So option C is the right answer. Now for the just a quick explanation to it. Pressure evaluation is often considered more difficult in incompressible flows than in compressible flows due to the nature of how pressure is linked with the flow variables and governing equations. In compressible flows, we were getting pressure very easily in the solutions because we got it from the equation of state. We did not solve it through the equations. However, it cannot be done in the same way in incompressible flows because in continuity equations, there is no presence of other terms except velocity. It is del dot u equal to 0. So, pressure evaluation is often considered more difficult in incompressible flows than in compressible flows due to the nature of how the pressure is linked with the flow variables and governing equations. And option B, incompressible flows have the property that pressure is not uniquely determined by the field alone, velocity field alone. This is because the incompressibility condition del dot V equal to 0 does not provide enough information to solve for pressure directly without additional boundary conditions or assumptions. So in incompressible flows, we have the property that ensures that pressure is not uniquely determined from velocity alone, because incompressibility condition from the continuity equation states that del dot V equal to 0. But there is no information about the pressure here, so we need additional boundary or conditions or some assumptions to evaluate pressure. In incompressible flows, the pressure field can be defined up to an arbitrary constant, meaning you can add a constant to the pressure without affecting the physical flow. However, this arbitrariness makes it harder to evaluate the pressure directly. So here what we are doing is that in incompressible flows, mostly what we do is pressure field can be defined up to an arbitrary constant. So we are giving some arbitrary values and we are just adding a constant values which doesn't affect the physical flows, but this arbitrariness makes it harder to evaluate the pressure directly. If you see actually solvers, fluid CFD solvers, especially in open form and all, there are different ways of defining the pressure, and mostly it would be like relative pressure, so and so kind. So this arbitrariness makes it harder to evaluate the pressure directly. And in contrast, in the compressibility flows, they are more straightforward in terms of pressure evaluation because pressure is tied to both velocity and density through this equation P is equal to rho RT, and for ideal gas, and there is less indeterminacy in compressible flows. Whereas in incompressible flows, pressure is strongly coupled with the velocity in the linear Navier-Stokes equations, but it doesn't appear in a straightforward manner. Velocity field is constrained by the incompressibility condition, and pressure is the Lagrangian multiplier that enforces the conditions, enforces this constraint. So it is Lagrange multiplier is similar to the one used in the optimization problems to find the local maxima or minima values. So this coupling makes solving for pressure and velocity iteratively more difficult as pressure has to be corrected in a pressure velocity coupling scheme. So what basically is happening is that in the question it was asked about pressure values, pressure evaluation. So we said that it serves to enforce continuity constraint, whereas it cannot be specified as a constant. So second statement is false, first one is true. So C2 is the right answer. Now, pressure evaluation, why it is difficult in incompressibility flows. That is what we are seeing. In compressible flow systems where density variation was there, what we were doing, we were getting the pressure through the equation of state. So it was very straightforward pressure calculation. Whereas in incompressible flow systems, pressure calculation is not straightforward, mainly because pressure and velocity is coupled in the Navier-Stokes equation, moment of conservation equation, but it is absent in the continuity equation. So the continuity equation becomes del dot V equal to 0 because density variation is not there. So this incompressibility constraint, incompressibility condition is being enforced. So this makes the calculation of pressure not very direct. So it is not a straightforward. So we are this makes the coupling more complex, and it accounts for the difficulty encountered in the getting the solution from the pressure velocity coupling. So this again, evaluation of pressure enforces the constraint of incompressibility, that is del dot V equal to 0. So we say that evaluation of pressure is not straightforward, it is complex in incompressible flows, and also del dot V equal to 0 because of the incompressibility condition uh, which is being imposed, like that condition should be satisfied. So that is making pressure evaluation difficult in incompressible flows. So for compressible flows, even though like pressure and velocity are still coupled like in this equations, the equation of state makes the relationship clearer. So there is less complexity in the indirect relationship between velocity and pressure. So that is the case. So yeah, that's it for today's class. Um, if there are any doubts, you can ask now. Yeah, PDF, it will be there, right? In the link provided, there is some Google Drive, right? So in that Google Drive, the PDFs are uploaded actually. The NPTEL provides that link for the video along with that in an Excel sheet. So in that Excel sheet, the Google Drive link is there. In that Google Drive, all PDFs are updated, and today's PDF will be updated as well. Okay, thank you. Um, okay, I'll close the session then.